Okay, shall I start?
Yes, sir.
Okay, very good evening to everyone. Okay, today I am going to give you a brief introduction about the frequency selective surfaces. Yeah, before starting this frequency selective surface, let me speak about little bit about the metamaterials, how the frequency selective surfaces came into existence. From the metamaterials, we all know that that is combination of two words. That is, one is meta and other one is materials. So the what do you mean meta? Meta means that the properties which are altered or changed by the human beings that are really does not exist. So the metamaterials are the materials which only exhibit a small subset of electromagnetic properties theoretically available. These are not practically available. So by altering some of their properties, we change a normal material into the metamaterials. So metamaterial can have their electromagnetic property that is altered to something beyond what can be found in nature. So these materials are not found in nature, but we have changed their properties so that they can exist and show some definite properties which we needed. Here we can achieve the negative index of refraction, zero index of refraction, magnetism at optical frequencies, etc. by using these metamaterials. Here, as we can see that the metamaterials, they are generally they are man-made structures whose wavelength is very greater than the homogeneous regime, as well as these are the artificial dielectrics which can be viewed as metamaterials. So by combining these the artificial media with unusual electromagnetic properties, here what properties? Permittivity, permeability, refractive index, refraction, reflection, propagation, all those properties which we can alter, and these way the man-made properties, these are altered, and these are the artificial dielectric which can be viewed as the metamaterials. So it started in from the Bose. So JC Bose here started his research in the 1898. This was the earliest research of metamaterials. Later on, Professor JB Pentry in 2000, he told about the negative permeability. He is just he was having his handkerchief on in his hand, and he was just looking something the light, and he saw that there are different colors of light are coming by the handkerchief. So he started his journey of metamaterials from there. Later on in 1968, Victor Veslogo, he told about that the electrodynamics of the substances with simultaneously negative value of mu and epsilon, but he don't know how they are getting. So what happened if a material when both electric permeability and the magnetic permeability are negative? So this was given in 1968 by Vector Veslogo. Then in 1999, John Pendry, he started using split ring resonators. Yes, you can see in the figure that the split ring resonators are there. So these are for the magnetism and conductors and enhance their non-linear phenomena. Here you can see that the sub-wavelength structures built from non-magnetic constituents, they are exhibiting an effective magnetic permeability, which can be tuned to values not accessible in naturally occurring materials. And he published his research in the IEEE Transactional Microwave Theory in 1999. Later on, in 2000, David Smith, just he put one strip line behind those structures which he has opened like the splitting resonators. So he experimentally demonstration of lambda is equal to 60 means for 5 gigahertz, and the metamaterial which is having epsilon effective is less than zero, as well as mu effective less than zero. So he rediscovery of the Visklagos paper that was here in 1968. So he proved here that whatever the Devin Vislago told, that was correct, and he actually proved by the experiment. Here the metamaterials are the artificial composite materials that is having the consisting of the structure very small, as we can see in the figure, then the wavelength of the incident radiation. These are the conventional materials. In the first figure, that the green structures, you can see that the atoms are closely spaced. They are put, and here you can see that these are the man-made materials. That here you can see splitting resonators are the units are they are made by the human being. whose size is very, very smaller than the lambda by 4. So from here, we can see that the permittivity can be positive or negative. Permeability can be positive or negative. Refractive index can be positive or negative. But simultaneously, without altering the properties, it cannot be happen. So what is going to happen if these properties are there? In the first quadrant, we can see that the conventional materials, they are having epsilon greater than 0 and mu greater than 0. So for that, the n is positive. So this way, it is the light is working is this way. It is bending towards the normal here. In the second one, you can see that the plasma and fine wire structures, mu is the epsilon is less than 0 and mu is greater than 0. So no transmission is taking place. As well as in this one, fourth quadrant, we can see that the epsilon is greater than 0 and mu is less than 0. So again, no transmission is there. Now here we come to both epsilon is less than 0 and mu is less than 0. So here refractive index comes to be negative. So the incident wave is going and it is coming back to the same medium. But in all other three, you can see that no transmission, as well as it is the transmission, it is going on the other side, that is on the conventional material. So these are the metamaterials from where both mu and epsilon are negative, as well as the refractive index, it is also going to be negative. One example of this is the bending of light is here. If the refractive index is greater than 1, then you can see that the little bit bending is there. You can see here from the figure, the line of sight is not there. But when the refractive index is 1 of both the things, at that time you can say the straight line, you can see that the whatever the material is put inside, that is shown. But when the negative means 1.3 minus 1.3, when the refractive index, you can see that negative refraction is there, and it is bending in a wrong way. So this is the property where mu and epsilon both are negative. So early metamaterials, they are relied on the combination of splitting resonator and the conducting wire post. Yes, you can see that one side the splitting resonators are there, and the other side are conducting wires or strip line, we can say that on the other side. Splitting resonators are used to generate desired mu for a resonant bank frequencies, as well as the conducting post, whatever these the strip lines or conducting posts are there, they are polarized by the electric field, and they are used for the generating the desired epsilon r for all the frequencies below a certain cutoff frequency. So by these splitting resonators, we can change our mu, and by using this conducting post, we can change our epsilon. So by combination of these two things, we can change the properties of the electromagnetic properties of the material, so that we can change mu and epsilon simultaneously. So here there are different shapes are the ELC, splitting resonators, everything is there. You can see here there are different combinations, and they are hence proved. These are some of the proven areas of metamaterials: the microwave clocking, the bending of electromagnetic waves using the graded indices of refraction. Here you can see that this is one of the example that is being used was some of the researchers. This has been also in the 2004. They are published in the front of the title of the Physics Today magazines. Here, that was D.R. Smith, and he has published in the Physics Review Letters in 2000. Like here, the conducting rod is there, as well as the combination of the splitting resonators and the conducting rod for the metamaterials. This is the first negative index materials. You can see here. And J.B. Pendry, he has told that this is the new field, and it was in 1968. The paper title was the electrodynamics of substances with simultaneously negative F and mu. V.G. Westlago, which I've told you in the previous slides. And then J.B. Pendry in 1999 and D.R. Smith, he has proven in 2000, and that was fabricated structures which has been proved. So there are some of the classification of the metamaterials, that the metamaterials are structures where single negative, double negative, and PVG media, they are structured, and the single negative where only mu and epsilon are negative, or double negative where both are negative. These are some of the examples of their, for the photonic band gap media. You can see that they are one-dimensional, two-dimensional, and three-dimensional structure. Single negative, that the ENG media, they are having mu greater than 0 and epsilon less than 0. The examples are thin wires, complementary split resonator structures, triple wires. For the MNG media, epsilon is greater than 0, mu is less than 0. So splitting resonator structures, spiral structures. So these are some of the structures by which we can get these properties. We can change these properties. For the ENG, these are the structures, some structures from where we can change these properties. Double negative, we can use the split resonators and wires, transmission lines, Masumi structures, all those things from where we can get the mu and epsilon both as a 0. Now we comes to the frequency selective surface, which is one of the thing like metamaterials, one of the classification of metamaterials. So frequency selective surface is a surface that is construction designed as a filter or EM waves. You all know that the filters are basically low pass, high pass, band stop, all those filters are there. So it is working as a filter and is transparent to the desired frequency band and reflecting at the other frequency. Means for some frequency they are transmitting and some frequencies they are reflecting back. As well as these are the periodic structures that are the having the same type of elements that are placed in either 1D or 2D. As shown in this figure, here you can see that the 2D structures is there in the X direction as well as in the Y direction. The same type of structures, they are being printed. There are some of the characteristics of frequency selective surface are they are very narrow band structures. They are periodic in 2 dimensions. We can fully describe the structures in the reflection or transmission coefficient. They are used for high power microwave applications. Initially, these structures were designed for the military purpose, but nowadays we can use anywhere these frequency selective structures. These are some of the basic principles which is working behind the frequency selective surface. As we all know about the properties of the light, that transmission, reflection, and absorption is there. In the first figure, you can see that if we are incidenting something, then this is being transferred to other side. So this is the transmission characteristics. Here in the reflection characteristics, we are just incident some light in the one of the material, then that is being completely reflected. And in the third figure, we are saying we are incidenting and nothing is being transmitted or being reflected. So everything is being absorbed. So these are the characteristic transmission, reflection, and absorption. On this characteristics, the frequency selective surface is working. Now we comes to the history of the frequency selective surface. In 1919, a patent granted to Marconi and Franklin, who used a wire section for tuning purpose, but cannot be called these structures as a periodic. Like this, you can see here. Later in 1974, a patent entitled Periodic Surface for Large Scan Angles was issued to Bennemonk, as shown in this figure. In this figure, you can see that the periodic structures are there. And there are some these structures which are copper or metallic. They are working as a L, as well as the spacing between them, they are working as a C. So inductor and capacitor, the combination is there. So in this way, the equivalent model of the frequency selective surface can be designed. Why this was introduced? The basic question is this. Initially, there was some drawback on the antenna. Like they are influenced by the presence of the ground. Like here in this figure, we can see that the antenna, this is the antenna. It is transmitting wave 1. But due to the presence of the ground, which is at pi phase shift, another wave is reflecting back from there. So it is showing the destructive interference with wave 1. So the gain and the properties of an antenna are not as per our desired results. So to overcome all these properties, the destructive interference, the frequency selective surface came into existence. So this here you can see in this figure, we have put one high impedance surface, which was frequency selective surface. Here the antenna is there, the wave 1, same wave 1 is there, which was transmitted by the antenna. By using the frequency selective surface in the place of the ground, you can see that again the second wave is coming, which now showing the constructive interference. Wave 1, wave 2. Initially it was showing the destructive interference, so the errors are there. Now it is showing the constructive interference, the distance between them very, very smaller than lambda. So this is the solution for the previous problem. High impedance surfaces are required. These are the high impedance surface, and high impedance surface artificial magnetic conductors of frequency selective surface are there, and so no phase shift is there, so the constructive interference is there. Now the use of FSS is not only limited to the antennas. They are used having very range of so many range of applications are electromagnetic waves transmit different types of data by using various paths. The devices use radio waves for communication. Those are cell phones, baby monitors, GPS receiver, Bluetooth devices, wire security instruments, microwave ovens. So many places we are now using these. Now, why we are using? There are some drawbacks of the wireless communication. So, to overcome all these drawbacks, we are using the frequency selective surface. They are going to reduce the interference in wireless indoor environment. They are maintaining the data confidentiality. They are maintaining system security. They amplify the desired signal and reduces the interference. These FSS are mainly used to filter out the unwanted interference. Means whatever the frequency we want to pass, that frequency is only allowed to pass, and other all frequencies are stopped. They are used as a spectral filter across the entire electromagnetic spectrum. Means it will make the signal protected, isolated, and separated from each other. Means whatever the desired signals we want to send, we want to transmit, that can be transmitted, and other undesired signals, they are stopped. Like in this figure, we can see that this is the ideal FSS wall. This where we can send the TV transmitter signal, TV broadcast signals, they can pass through the walls. This is FSS wall completely where we have put the frequency selective surface structures all over the room. It is blocking outside signals like potential security threats, like the signals, they are blocking it. As well as inside, you can see that it is also blocking the inside signals so that they cannot go outside. Means FSS wall confine internet signals, block unwanted internet signals. Here they are blocking the unwanted internet from outside, as well as they are not sending the inside signals to the outside as well. So this is the electromagnetically designed buildings which can protect our data, that should be confidential, as well as no one can interfere with your signals as well. There are some of the factors which are influencing the FSS performance and design. Here, the conductivity of the FSS conductor, geometry of the FSS element, permittivity of the FSS substrate, period and number of the FSS array in cascade configuration, the electrical distance between the FSS arrays, choice of element type, which type of element we are going to use by designing the FSS, the metallic frames surrounding the FSS window. So these are all are the factors which are influencing the performance and design. Now the FSS is classified into basically two types. One is the passive array and the active array. This is one of the experimental setup which are being used for measurement of FSS without the anechoic chamber. Later on I will show how inside the anechoic chamber the measurement is being done. The passive array. The passive array, that is electromagnetic radiation from antenna, will work as a source, as shown in the figure. Is here figure you have seen that the one antenna that is working as a source, and they don't need electric source to power the work. Here you can say this is only the surface frequency selective surface structures here. It doesn't require any of the power to work. Now coming towards the active array. In the active array, each patch is fed or excited by the individual source of the source generator and the same power amplitude as shown in the figure. Here you can say that each element that is given a power source. And it's become the drawback that the total cost of the setup and weight has been increased, as well as it sources they again shows the interference on the signals. So maximum time we are using the passive arrays only. On the basic arrays. In the finite array, The effect of size and the edge of current that induced on the FSS and on radiation performance of the antenna. Also, the number of elements repeated in an X and Y direction, they are fixed. As I shown you in the previous figure here, they are fixed. It can be used for very, very small places. But in case of infinite array, it is maximum number of elements or unit cells we can use. The number of elements are repeated in X and Y direction are infinite in numbers. Only a unit cell is required to be simulated and will represent the whole array. Here you can say that a single unit has been designed, and then we are taken by studying all those properties. We are designing a array, infinite array of this type. On the basis of construction, material and geometry, they are again classified into low pass filter, high pass filter, band pass filter, and band stop filters. Here, I've shown you some of the geometries or the filter geometries, like the low pass filter and high pass filter. Here you can see that this is the mesh type. Here, this is the brownish part which we are showing, that are metal. And this is a inductive mesh filter. And here you can see that this is the response frequency as well as the transmission. In the capacitive mesh filter, you can see that the response is just opposite. And you can see that the both structures, one is inductive mesh and the capacitive mesh, both are the complementary of each other. That's why the results are complementary of each other. Here you can see directly. For the band pass filter and band stop filter, again the same thing is going to happen. Here, one band is passing and one band is stopping for the transmission as well as the frequency response. Here, both structures are again inductive cross mesh filter and the capacitive cross filter. Both are again complement to each other. So their results are again complement, and one is transmitting as well as other is not transmitting at the same frequency. You can see here from the frequency response of the band pass and the band stop filter. Here you can see that the band pass, this here structures that the gray part, that is the metallic part, as well as there is the white part, that is the hollow part. So only a specified band is transmitted. Here you can see that a specified band that is being transmitted, and the rest all other bands are being stopped. Similarly, for the band stop filter, you can see that the only this band, that 3.41 gigahertz, that is being passed, and the other bands are being stopped. The FSS are again classified into two types, planar and non-planar. Planar FSS are the printed circuits on the substrate. They are loaded or unloaded elements, single or multi-layered. Now the non-planar, they are periodic, dielectric shapes, cross-layer connected elements, photonic bandgap structures, as you can see here. These are the example of planar FSS elements. Here, the center connected elements, they are planar. Loop elements, again, solid interior elements, and the combination of different types of, it is shown here. So these type of elements can be used for designing the planar FSS elements. Not only these, any of the shapes you can design in the planar. And these are non-planar FSS. You can see here, they are in X as well as in the Y direction, or in the Z direction also there in some of them. These are dielectric grids, normal photonic band gap, wood pile step, photonic band gap, and the loaded metal. Here you can see that the multi-layered structures are there. So these are non-planar FSS. Here, the working principle of the FSS. Here you can see that in the case one, the incident is there. Here you can see the polarization is vertical is there, so these signals cannot be, due to the induced oscillations and the low transmission, here the signals cannot be passed. But here, due to the high transmission, the signals can be passed through the surface. So this is used for the stopping, and this can be used for the passing the signals. There are some of the advantages of the frequency selective surface. The angular stability with respect to incident angle. Here, angular stability is a very important term in case of frequency selective surface, because this mostly we are using the passive elements. We don't know where from where the signals are coming, either from 0 degree, 10 degree, 20 degree, 30 degree. So we have to put our structure should be angularly stable. Our structures can be angularly stable so that it can stop the signals or pass the signals coming from any of the directions. Next thing is improved impedance bandwidth. As in the first figure, I have shown you that it is showing the constructive interference. In the constructive interference, it is improving the bandwidth, because at the destructive interference, the gain as well as directivity or some of the other parameters, they get affected. But by the constructive interference, the bandwidth may increase. Here, the improved impedance bandwidth by using the frequency selective surface. High impedance matching is there. Shielding of the antenna, so that the signals cannot be go or they can not give the back radiations. The radiation efficiency is also increased by using these frequency selective surfaces. Now here are some of the designs. A compact frequency selective surface based band stop filter for W-line applications. Here I will tell you how to design, how to get our desired results by using some of the formulas and by structures, how to get our desired results. Here we want to design a stop W-line band 5 to 6 gigahertz. We have taken the material Teflon, whose dielectric constant is 2, and height we have taken for 2 mm. Let's decide the dimension of the substrate. You know that is the general formulas which are being used. L is equal to lambda by 2 epsilon r. So by using these formulas, we have calculated the resonant frequency, which comes to be 5.5. And then the patch shape size is approximately, by simulation, we got 16.5. So the proposed FSS is 0.35 lambda into 0.35 lambda. This is our unit cell, only one square unit cell we have designed. So we are not getting the desired results. This is the front view, and these are the some of the results we are getting. Then we have gone through the surface current without any slot. Here you can see that some of the at higher frequencies we are getting some red that surface currents. So we want to resonate our at 5.5 gigahertz. It is resonating. You can see here it's resonating at higher frequencies, and here at 5.5 gigahertz we are getting some of the surface current. So we optimized and we have cut a slot in the between. Then we are getting this type of results again. Then again we have gone for the different surface currents. Then again for T mode, for TM mode, we have just now we have calculated the resonant frequency by using general formula. For the fundamental modes, we have gone this. For the first order mode, we have just that's why it is showing the 3 for the, you can see here. Then for the second order modes, everything we have optimized the dimensions, and we got our desired results. Now we come to the equivalent model for these type of structures. So the general equivalent model of the frequency selective surface of this type of structure should be L and C should be in series. Here you can see this type of structure should be there, and these values can be calculated by using these formulas. Everything is given. The X from the PWD, that is the periodicity, width of the loop, as well as the lambda operating wavelength. From here we get these desired frequencies, and we can directly get these values, and by using these values we can directly calculate the final frequency, and from this we can do the equivalent circuit analysis. And from doing the equivalent circuit analysis, we got the 5.42 gigahertz, which is approximately near about 5.5 gigahertz. So we have just started from this structure, from calculating the value in this one, and then we have simulated structures, and then after simulated we have gone for the equivalent circuit analysis, and then again we are getting the similar result, and this is the array designed for the same structure, and these are the final results, simulated results, which is showing for the 5.5 gigahertz. You can see here for the T mode as well as for the Here you can see that all the three results, transmission, absorption, and reflection, are being combined. We can see here that the reflection at 0 degree, transmission at 0 degree, and the absorption at 0 degree. Here you can see that the perfect results we are getting at 0 degree. In the another design, we have stop W band as well for the same thing. Now we we are going for the different types of structures. Initially, we have gone for the square structure having a slot in between. Now we gone for the other type of structure. Here you can see that the L type of slot has been cut. So we are getting one band at approximately 6.4 gigahertz. Again, same structure, just we have rotated. You can see that just we have rotated it. Inverted L type. This was L type slot and this was inverted L type slot. Both the structures, because when we are rotating, the structure should be looking similar only. If I rotate this structure into 180-degree, both structures are similar. But when we combine these two structures, at that time, we are getting our desired results. Here you can see that we have combined and we are getting the desired results at 5.5 gigahertz. And these are the optimized dimensions for this. And again, here we have calculated the equivalent circuit model by using these formulas, because these are the structures that are having. And by calculating, it is frequency is coming to be 5.8 gigahertz. And here our frequency was coming to be approximately 5.7 gigahertz. So again, we have just simulated, calculated, as well as from the equivalent circuit, we have analyzed the things and we got the same results. Yeah, I was talking about the incident angle variation. Here you can see that we have varied the incident angle from 0 to 90 degree. For each and every angle, we are getting the same results. Here you can see that by rotating the structures on that the incident angle, we can get this type of results. Again, the transmission, reflection, and the absorption result, they are being combined here, so that you can see that all the five working on 5.59 gigahertz. Here in the red part, you can see that the reflection part, green part, that is again showing the transmission part, and the blue part, that nothing is being absorbed, fully pump part is being reflected, only this is transmitted. Here we are working for only single band. Now we are moving towards the dual band. Design and analysis of polarization independent dual band pass frequency selective surfaces. This is one of the articles that was published in the International Journal of RF and Microwave Computer Aided Designing. Me, Professor M.M. Sharma sir, and Dr. C.P. Jain, he was a part of co-author in this journal. Now, again, I'm telling you about the stepwise designing, how we are started this. Initially, we have started from one of the square ring. Then we make one plus shape ring. Then we have combined those two, because from one structure we can get one frequency. From two structures combining this, we get the two frequencies. Then we have taken one of the plus shape. Then we have combined and just tuned so that we can get our desired results. So this is the final structures we have. For the first one, we are getting the resonant at approximately 1.8 gigahertz. Then here, by combining these two, we are getting the two resonant bands. Then from this one, and by combining here, you can see that we are getting the two, one band here and one band here. As I told you, here we are going to band pass, dual band pass, two band pass are there. So in the last figure, you can see that the two bands are passing. One is this, is because this is a transmission, one this band and other one this band, 2.5 and 3.5 gigahertz, they are being passed here. And this is the final proposed structures with optimized dimensions. Here we have optimized dimension to get the desired frequencies. This is the results for the TE mode, transverse electric mode, and by rotating 90 degree, we are getting the same results in the TM mode as well. Because by rotating the 90 degree, the structure is symmetrical, so no results can be changed. Here you can see that the surface current for the 2.5 gigahertz, that we are getting the 2.5 gigahertz from the which places, and for the 3.5 we can see that from the internal part we are getting the 3.5 gigahertz frequency bands. Now these are the band pass. So band pass structures having this type of equivalent circuit. Here we are having the two rings, so we are getting these type of structures, and these formulas L and C are being calculated from these, and these results have been analyzed using the ADS software as well. So from where we get these parameters, and again by using these parameters we have find the resonant frequency approximately near about here 2.34 and here 3.84 gigahertz we have calculated by using this. And this is the photograph of the fabricated 15 cross 15 element of that structure, and this has been measured inside the anechoic chamber. Here you can see that the two antennas are being put, and in the between the structure is put, and you in the bottom you can see there the protector is being put, so that the angular incident angles can be calculated, or how it is showing its properties. Here the measurements results are being shown, simulated and measured, they are being compared, and they are in good agreement. Here you can see in the figure, as well as for the TM mode the little bit variations are there. And for the theta, for the incident angle variation, that is also being shown here, but at our frequencies we are not getting any of the variations here. These are the two our transmitted frequencies, we are not getting any of the variations there, and these are for the TM mode and those were for the TE mode. Now we are coming towards the tri-band. Initially we go for the single band, then for the dual band, and this for the triple band. Again, this is a research paper published in the Peers in 2021, a polarization insensitive tri-band bandpass from frequency selected surface in WiMAX and W-line application. This is the final structure which we have proposed. Here you can see that these are some of the simulated 1, 2, and 3. These are the three frequencies: 2.5, 3.5, and 5.5. These are the frequencies which are being transmitted for the TE mode as well as for the TM mode. Here you can see that from the outer point we are getting the 2.5 gigahertz, from the little bit in the middle part we are getting the 3.5, and from the center one, that is the plus shape, we are getting the 5.5 frequency. Here three rings are there, so we have proposed this type of structures, and again we have just calculated the dimensions. So from here you can see that 2.49 approximately 2.5, 3.4 that is approximately 3.5, and 5.6. By using these parameters we have calculated all these things. So again we have fabricated the structures, we have measured the structures inside the anechoic chamber. Again we have measured the results. We can see that the results are also again in the good agreement. So we have simulated, measured, also we have analyzed the results using the ADS tool or equivalent circuit analysis. So everything is coming in good agreement, and again we have changed the incident angle from 0 to 45 degree. It is now showing very good agreement here. We have gone to single band, dual band, triple band. Now we comes to the another design, how we have come to the 4 bands. This design has been published in the International Journal of Microwave Computer Aided Engineering in 2021, I think. Yeah, 2019. This design is the final design which you can have shown in the figure. Again, the stepwise designing is shown here. Initially, we started from a square ring. Then we have gone for a H type of ring. We have modified this ring like this one. For this one, we are getting this type of results. Then for H type structures, this type of results we are getting. And by varying the ring, this type of results we have got. Now this structures, I am getting the two bands, one this one and other one this one. But I needed the four bands, and the structure should also be symmetric. If I am just rotating this structure to 90-degree, then it's going to be I type. So H and I, they are not symmetric. So we have proposed that by the combination of H and I, like this one, H, that I that is being rotated 90-degree, it becomes H, again rotated 90, I and H. And we have combined this structure to make one unit cell. Now this complete structure is single unit cell. We have combined and make it one unit cell. Now by rotating 90-degree, again it's look like the same. So this is the final proposed structure. You can see that for the I result is different, and for the H the result is different. And by combining these, combining two in such a way so that we are getting our four bands. You can see here 2.5, 3.5, 5.5, and here you can see that we are getting the four band is where TEM and TM mode. 2.5, 5.5, 8.6, and 10.9 gigahertz. We are getting the. Also, we have seen the simulated surface current for the proposed designs. That 2. We are getting from where we are getting these frequencies, like 2.5 gigahertz we are getting from the outer surface, 5.5 we are getting from the here these diagonal elements, 8.6 we are getting from the outer, as well as the 10.9 from the all the elements, combination of all the elements we are getting. This is the final fabricated structure. You can see here this is a photograph of the final structure, that is a combination of H and I. Again, it has been measured inside the anechoic chamber. These are the measured results, and they are showing good agreement here for the TE mode, also for the TM mode. Also, we have gone for the angle variation for the TM T as well as for TM mode. That is, it is giving good angle variation up to 45 degrees. So for the TE mode as well as for the TM mode, we have gone for the angle variation as well. Now we comes to the 5 bands. We have gone for single band, dual band, triple band, and now we are going for the penta band, means 5 bands. And this paper was published in IEEE Transactions on Electromagnetic Compatibility. Me, Professor M.M. Sharma sir, and Professor C.P. Jain, they are my co-authors. The title of the paper is Smartphone Frequency Shielding with Pentaband Stop Frequency Selective Surface for Security and Electromagnetic Health Applications. In this design, we have used all the frequencies which are being used for the smartphones, starting from first frequency that is being used for the 900 megahertz, second frequency which is used for the GPS 1.5 gigahertz, 2.5 gigahertz, 3.5 gigahertz, 5.5 gigahertz. These are frequencies we have used here, which are being used in the smartphone. Now these are the step-wise designing, how we started our work and how we got the results in this design. Again, we have started our designing from the square ring. We have calculated the length from this formula's length and width. And we have simulated this results, and we are getting one single 1.5 gigahertz. Then we have altered the ring. Now we are getting the second one this way. Now we have just combined these two in this way. First and second, we have combined, and by combining these two, we are getting this result. Means by combining two rings, we are getting the two bands. Now these two bands are being combined. Then one more ring, that is altered ring, is you have seen that has been, we have simulated that. Again, we are getting the 3 gigahertz. Now, initially there were 2 rings. Now we are combining those 2 previous rings with this ring. So the structure will look like something like this. And its simulation results will look something like this one. Here you can see that now we are getting the 3 frequency bands. One is 1.5, second one is 2 gigahertz, third one is 3 gigahertz. We are getting the 3 frequency transmission bands. Now again, we gone for the 4th ring. For that, we are getting approximately 4.5 gigahertz by simulating that only frequency. Now we again going to combine the previous 3 rings with this ring. So we have reached to the 4 rings. And we are getting this 4 bands. Here you can see 1, 2, 3, and 4 resonant bands here. Transmission bands, we are getting 4 by combining all the 4 rings. Now we comes to the 5th ring. It is resonating in 5 gigahertz. Then again, we are going to combine the 4 ring and this ring. 5 rings we have combined, and the structure will look like this structure. And then for optimizing our results, we have put one patch in between the rings. This patch, in this, we are going to, in this figure, having 1, 2, 3, 4, 5 rings, we are going to combine this patch. So our final structure look like something like this one, and its results are for the 4. We are getting these types of ring, but our results are not as per the desired. So after putting this ring in middle, we got our desired results. And this array, we have make the proposed array of 11 units. And the equivalent circuit model for that unit cell is like something like this one. And we have just simulated this array in the ADS tool, and we have got our desired results by calculating by those formulas. I have also told these formulas in the previous slides as well. So by using these formulas, we have just calculated our values, and approximately nearby we have reached those values. 1.5 nearby 1.44, it's 2, 2.65, 3.4, 5.46, approximately nearby we have got the result. And these are the simulated results we are getting for the T mode as well as for the TM mode. We are getting the 5 frequencies. And these are the surface current for all those frequency: 1.5 gigahertz, 1.8 gigahertz, 2.5 gigahertz, 3.5 gigahertz, and 5.5, from where we are getting those resonance. This is the fabricated structures of these pentaband frequency selective surface. And this is the again the same setup we have used for the measurement of the frequency selective surfaces inside the anechoic chamber. Also, again, the structure is symmetrical. As we can see, this structure is symmetrical. You can see here, if we rotate this 90 degree, again, the structure will look like similar. No changes are there. One thing we have to remember for making the angular stable structure, the structure should be symmetrical here. So here you can see, if I rotate 90 degree, then the same structure should be there. That's why, again, we are getting the angular stability. Here you can see that the up to 45 degree, we are getting the angular stable structures. So these type of structures, they are having the ability to efficiently transmit high energy signals through very small apertures. With the apertures, you can see that very, very small in terms of 27 mm, 30 mm, 40 mm, only this one. And it can efficiently solve the interference problem in coexisting channels, these type of structures. They can provide both mechanical and electromagnetic protections to the antennas because they are of made up of very hard materials. Also, we can change our materials as our need. We need to design the different designs for different applications, and this is because we are living in the wireless world, so the demand of frequency selective surfaces is increasing in future as well. The polarization independent multiband frequency selector will be the key solution for band pass or band stop for the frequency bands. As for of your frequency, as I have designed something for 2.5, 3.5, 5.5, again for the 5 frequencies, 4 frequencies, everything I have designed here. So the design of the analysis of the polarization independent multiband FSS is being carried out. Here for the single-sided polarization independent frequency selective surface, they are being designed, analyzed. They are using the single band, dual band, quad band, and pentaband. Here we have used. I have shown you about the stepwise designing and development process, how these structures are being designed, how these are analyzed, and how these parameters are being investigated, and how these structures are miniaturized and made the polarization stable. And then we have compared the results with the simulated results, with the equivalent circuit analysis, with the analytical results, also verified with the fabricated results inside the anechoic chamber. And these structures, frequency selective surface, are being used for the communication systems, and these are the miniaturized designs. And most of the structures, they are showing the incident angle variation from 0 degree to 45 degree for both the TE modes and for the TM modes. And we have also seen that they are showing a very good agreement for the simulated as well as for the fabricated results. Now coming for the last structure, which is the pentaband structure. It is using all the frequencies which are being used for the our smartphones. And these structures can be escaped from the unwanted radiation during the voice call. If these pentaband signals, if this FSS, pentaband FSS is being used on your smartphones, so it will block all the frequencies so that the radiation from those smartphones cannot come to you. There are some of the safety issues in the case of FSS. This FSS element should be able to dissipate heat properly. So proper consider thickness of FSS. Pick low loss dielectric to reduce the heat, because some signals being transmitted, some absorbed, and some are being reflected. So the energy is not being destroyed. So in either form of heat or in form of reflection, it is going somewhere. So we need to choose a dielectric so that it can reduce the heat. We have to select the material that have similar coefficient of thermal expansion as well. We have to choose the material having the high thermal conductivity. We have to choose the voltage breakdown should not occur due to the applied electric field. We have to remember that. To avoid the higher order mode dispersion, the dielectric with low relative permittivity would be best. Now I'm showing a little bit some of the things that the applications of FSS and metamaterials. This is electromagnetic clocking, which is the principle of invisibility. You people have seen one of the initial of the Physics Today magazine. I have also shown that this is the metamaterial, how the electromagnetic clocking has been started. So by putting this way, the signals are being clocked. Like here, tearing the space, conformal space. Like here, you can see that the straight line is there. By tearing the space, again, whatever the signal being transmitted, and that we are going to receive at the end as well. So whatever in the between the tear the space, this way the invisibility came into existence. This is the electromagnetic clocking. Here you can see that in the simulation, whatever the wavefront is being transmitted from here, the same wavefront is being received in the simulation, as well as in the experiment. You can see that only very little deviation from the incident is there. So in this way, anything is between this circle, that is being invisible. Here you can see that the electromagnetic invisibility from the first figure, second figure, and third figure. You can see here the person is there. If he is under the electromagnetic invisible means this clocking, then he can made be invisible. Here some of the news articles are there. Terahertz radiation and metamaterials combine to form X-ray specs. We see from the only using the X-ray specs, you can take the X-ray, you can see inside the body. You have also seen the movies, the irresistible fantasy of an invisible man and machine. So every concept has been taken from here. Whatever the concept of the electromagnetic is, they are being used by the people. This is the best example, the chameleon. He can change his colors, means he's changing the refractive index. How the refractive index is being changed? By changing the properties. He is just changing the properties so that he can hide. The chameleon can hide, he can change his colors according to the environment. The steel fighter that is invisible to radar. Here the absorbing paint is again the properties of the metamaterial are being used. Mu and epsilon are being used here in this case also. Here when a people is standing on the front of this projector, here you can see that he is wearing some of the clock material, and that is being, but the signal is going to the screen as well. Here you can see that Fantastic Four, the movie, the Invisible Woman, again one of the example of the electromagnetic clocking. Everywhere the electromagnetic properties or mathematical properties are being used here. This is again the Invisible Man by H.G. Wells. The concept again is the same, change in the refractive index, velocity of light in free space, and by using these properties we can go for the mu and epsilon. Everywhere it is the principle. Mirage, we have studied from our childhood how it is happening there. The bending of light due to the gradient in the refractive index. These are some of the more applications: absorbers, antennas, super lens imaging, clocking, solar cells, invisible submarine. All those are the examples of the metamaterials. So there are so many things, so many areas to explore all these metamaterial things. Chiral materials, negative index, artificial magnetism, switchable metamaterials, amplifying metamaterials, sensor metamaterials, quantum metamaterials. So many things are there. Okay, with this I stop my talk. Thank you for just listening me, and if any queries are there, please let me know.
Participants, you are requested to kindly ask the questions if you have any queries. Sir, there are few questions. May I say, sir, the question? Ask the questions.
Yeah, just I'm checking on that. Yeah, chat. Yeah, I'm just opening the chat box. Yes.
Sir.
Yeah, so many questions are okay. I'm starting from the first question that is asked by Mr. Ankush Srivastava.
Yes, sir.
Do we call a combination of split ring resonator and conducting wire a metamaterial, or split ring itself a kind of metamaterial? By split ring resonator, by combining both, we can change the properties of mu and epsilon. By only the single thing, we cannot change both the properties. So by the combination of the split ring resonator and the conducting wire, we can only change the mu and epsilon. So that is if we want to change the mu or we want to change the epsilon single, then we can say that from the split ring resonator or a conducting wire. But if we want to change both the things, mu and epsilon, then we need to combine both the things. Second question: difference between high impedance surface, frequency selective surface, artificial magnetic conductors are the same. Not necessarily they are same, but they are a similar type of things. High impedance means that is having a means that is the surface which is having a very high impedance. Frequency selective surface, that is depend on the desired frequency it is passing and desired frequency it is stopping. Artificial magnetic conductor means it is working for the magnetic properties only. But similarly, we can say we can change either by name by changing little bit of their properties. For the slide number 76, okay, just I'm coming to slide number 76. Yes, in the slide number 76.
Sir, actually, I wanted to ask for the 77, like multiple resonants are there. So
Yeah.
can we, how to get the wideband, sir?
For getting the multiple resonances, so you can put the spacing between those and adjacent elements so that they can combine the small bands. They can combine, and you can will get the wide bands. Like here in this structures, their structures something like this one. But I want to get wide band. Then I can combine, or I can put another rings structures, and they should be very near. The spacing is very near, so that the resonance, like one is resonating in 1.1, other one is resonating in 1.2, third one is resonating in 1.3. So we combine and we are getting from the 1 to like 1.3. This way we can just do it.
Okay, sir.
And the next question is, what is polarization insensitive in it? Polarization insensitive means like by changing the angles, it is not changing its properties, like either the transmission or reflection, that is not being changed. If we are incident, the as I told you, we don't know where the signals are coming. We cannot see the signals. So if we are putting our the periodic structure in somewhere, that if the angle is 0 degree, 10 degree, 15 degree, 20 degree, whatever the angle, so it should say, give the constant resonance there. So its angle can, so from the angle we are not, our results should not be changed. That means the polarization insensitive. Or one more thing, if we are going to change from TE mode to TM mode, means 0 degree to 90 degree, or 0 to 4, we are just changing from TE mode to TM mode. At that time, the structure should be symmetric, so that by changing by the orientation of the structure, our results could not be changed. Suppose I need to design a polarization sensitive antenna, then how much maximum we can vary? That if you are getting up to 90 degree, that is very good. But that is 45 degree, 50 degree, that is sufficient for the things. Vikram, so how can we calculate shielding effectiveness? For shielding effectiveness, we have to check for that transmission. We have to go for the transmission, and from there the transmission, how the signal is being transmitted by and then how much signal is being reflected back. From there we can calculate the our shielding effectiveness. How to decide the size of array units so that we measure the level? That depends on the size of the antenna, because where you are just putting your FSS complete structure, like this structure I've shown you in the slide number 1. If it is complete, the complete phase, physical face of the antenna, so that the signals cannot go beyond these sides, so that you can see which signal is passing, which frequency is passing, or which signal frequency is being stopped. So the size of the your FSS array should be bigger than the phase of the antenna from where we are going to measure. Sir, I observed that you have focused most work on the multiband. Why are your thoughts on broadband with greater signals multiband? Here we can go for the multiband as well as for the broadband. That depends on our applications. For multiband, where we need to transmit some signals, we need to stop some signals. But in the case of broadband, we will go for the complete band or for a single band like this one. But nowadays, you people can see that the single everyone using the multiple frequency. Your smartphone using 5 frequencies, your Wi-Fi is using 2.5, sorry, 3.5, 5.5 gigahertz. All those things are using. Also, so many things are there. That's why depends on our applications. We can go for the multi-band as well as for the broadband. What is the importance of surface current? How to analyze it? What is infer from it? From the surface current, we can see that from where we are getting, from which part of that your element we are getting these frequency resonances, so that we can alter those, so that we can change the path of the current, so that we can increase or decrease the path. So we are getting the our desired frequency, or we can make it wideband or stop wideband or smaller band. All those things we can do with the help of the surface current. How to simulate an array on universal CST, because the flow port simulation is not used. Please elaborate. In the CST, we are going to use the flow port simulation, and for that, you need to design array, and from the array you can simulate it. But only the things you need a GPU or very large RAM, or also it is taking so much of time for their simulating. I have simulated the that array inside the CST using the flow port analysis as well. Also the flow port analysis that is considering the infinite cells in x direction, also infinite cells in the y direction. That's why we are using a single unit for analyzing the frequency selective surfaces. What will electrical equivalent circuit in slide 101? Okay, just I'm coming to 101. Here we have not designed, but we can just make a capacitive combination of the capacitive and inductive circuit, and finally, as depends on the we are going for the stop band or pass band, as I shown in the previous figures here. This is equivalent circuit for the. This is band pass. For the band pass, we are using this type of structures, and the band stop, the L and C are in the series. So this way, these are the combination of the different types of structures. This is the final equivalent circuits which we are getting. Please explain the formulas used, because 91. Okay, here
Hello,
you can see there
hello,
for,
hello.
yeah, Hemant,
Uh, Good evening, sir.
very good evening.
You are using the four orthogonal element.
Yeah,
Then you are putting the one decoupler between them. Then, sir,
okay.
how to electrical equivalent circuit you will design? What is the
That
mean by
depends on the which
decoupler?
type of like here in this structure. Just I am telling you, in this structure you can see there, like this is your
I
conductor, from the
Yes,
conductor to different other conductor. If I'm coming from
yes,
top to or right to left,
yes.
so from here, that is conductor, then capacitor, then conductor, then capacitor, then conductor, then capacitor, all those things. So similarly, we are just going to make an equivalent circuit, and which comes to be in this form only. So for different rings, we have to combine it and take it this form, because we are having the formulas for this format only. That's the main reason for, so that we come for this one. How to
In
calculate
slide
the here? Yeah,
in slide 102,
102.
102.
Yeah,
This is 92, sir. 102.
yeah, this is 102.
The slide is not moving.
At my place, it's 102.
Yes, you are. Yes, 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 yes. You will see this diagram. One decoupler is used.
Okay.
Decoupler. Then what will be the L and C combination for decoupler? If you will do an electrical equivalent circuit, then which element will be used between the two cell or two unit cell?
Hemant, your voice is very, very low. Little bit can be louder.
Hello, sir. I want to ask that suppose you are using the as a decoupler between the unit cell
Okay.
element.
Okay.
Then, sir, then what will be the equivalent circuit? This decoupler only.
Oh, for your unit cell, you can make one equivalent circuit. For the decoupler, you make another equivalent circuit, and you can combine those only.
Not individually for decoupler equivalent circuit.
No, you can combine both, and finally you can analyze it in the CST. Oh, sorry, in the ADS. You can make,
Okay.
if you are just using a unit cell, then in the unit cell you can consider all those parameters in the unit cell as well.
Suppose this is any patch antenna. Then
Yeah.
this is the decoupler between patch antenna. Then how
Okay.
to calculate how to design the electric equivalent circuit?
In the if you like you are placing the FSS in the ground, then equivalent circuit of the FSS in the ground, then then your substrate, then the means copper is there, then your patch, then it is L element is there, means L is with the C, and your complete FSS structure is there. Like this, you need to do for that. You have to combine all this.
It's simple. Just I am want to ask you just a simple antenna that is
Yeah.
connected in orthogonally. We are putting
Okay.
the decoupler between them for a reduce the mutual coupling.
Okay.
Then how to design the
Then you
electric
need to
equivalent circuit?
you need to use the for that capacitive element in the between.
Only capacitive element.
Yeah, only capacitive element, but for the
But
mutual inductance, little bit L can also be used.
because you are using the inductor na, between them.
Yeah, that's why the L can also be used
The LNC in
for there,
series
because
or
the
parallel?
mutual inductance is there, so L will also be come in
The
picture.
LNC
L and C will
in
be there.
series or parallel?
Yeah,
LNC
and that depends on
series
the
or
which type
parallel?
of structures. That depends on the by seeing the structure only we can comment. Without seeing the structure, we cannot comment on that.
Okay, suppose simple microstrip patch antenna then.
Yeah, yeah.
Simple microstrip patch antenna, one rectangular shape and the feed line. Then it will
Hmm.
connect in orthogonally. Then
Okay.
what will be the
Okay.
LNC?
Yeah, that C and L both will in parallel.
Both will be in parallel. How to
Both
decide,
will in
sir?
parallel.
How to decide?
Because when you are just changing the orientation, like orthogonally, you are just placing at that
Yes,
time
sir.
the C you can see the directly, but L that is due to a mutual, and both are in parallel at that time, and the ground both are having the ground in same.
Yes, sir. Ground is
So
same.
ground in same. That's why it's going to be parallel. Ground is common in both of the things.
Yes, sir.
Yeah, that's why.
If ground is DGS, then
The defective ground at that time.
yes, sir.
No, note at the ground is defected or the ground is different. Both are ground is defected, but the ground is same for both the things.
Same will be.
Ground is same for both the antennas. No, either it may be defected or it may be complete ground. There should be one ground. That's why we can just only comment by using the complete, uh, by studying the structures only, without seeing the structure or without, so that we cannot comment on it.
Okay.
Okay.
Thank, thank you,
Later
sir.
on, we can discuss it in detail.
Okay, sir.
Okay. Uh,
Then, sir,
Please
one more
provide the
question.
reference for all the
Sir,
formulas other than bank. There are so many papers are there. Abhishek, there are so many reference papers are there. So from there, you will get these formulas. Now the one metamaterial book is also there. I didn't really remember the name, but the metamaterial book is there. Reference to metamaterials book is there. From there, you will get the formulas. In case of absorber for shielding effectiveness calculation, how can we calculate S21? Because generally it is 0. Yes, it is 0 in case generally, but practically it is not 0, because S21 we are just considering, in case of absorber we are considering that the copper sheet is in one side, but do you think that all the signals are being stopped? So at that time, very less signals, they are just penetrating it and they are being reflected or transmitted. The signals are being transmitted. That's why. That's the main reason for getting the shielding effectiveness. One example for if you are just inserting any of the, if we are putting one plate, that plate, copper plate, that will radiate. If it is radiating, means something is being coming out of that box. So from there we can calculate it. Okay, Vikram, got it? Any
Yes,
other
sir.
questions?
Sir, how to hello? Sir, how
Yeah, yeah.
in metamaterial we are using the polarization conversion ratio (PCR). Then how to
Yeah,
calculate PCR? Then
that I have not used
polarization.
here. That I not currently I'm using here. So later you can do, we can discuss individually it. Okay.
Okay, okay, sir.
Okay, Manth. Yeah, these are my
Yes, sir.
details. If you are having any of the queries, you can put or you can send it to my mail ID or you can call me.
Sure, sir. I will contact you. Thank you,
Yeah,
sir.
in slide number 98, how you get to know where the design 98. Okay. Hmm. We have started, Abhishek, we have started from here, from a ring. We need to go for our desired results. Means I need this one. By using this design, I am getting this type of result. So by altering or by changing, that is coming to be hit and trial, because we cannot calculate the complete things. That something is going to be hit and trial here. So we got by using, like if I am just bending it shape, I am getting the little bit of our result is shifting. All those things we are getting by the hit and trial, because we have to tune it. So for tuning, no calculations will be used. That's why the design is being altered. And for making the or for making the complete structure polarization independent, we have just done these things for 1, 2, 3, 4 for making, so that we can get the polarization independent structures or the angular stability here. Okay. Okay. Thank you.
Hello,
Any more queries if there?
sir, just one basic
Yeah.
question.
Yeah. Tell me.
Sir, actually, I'm a research scholar and I'm currently starting off in this journey.
Okay.
So, when we want to design something, sir,
Okay.
what would be the systematic approach that you can suggest me, sir? Like,
Okay.
because
Just
mostly
I am
I seem to be
here. I have
com-
started. I have told you here. Just I'm telling coming.
yes, sir. You have taken
Yes.
from look, then step by step.
Yeah. Here. I want to design this. First, I have to calculate I have to know about the substrate, dielectric constant, height, everything. Then I need to calculate the dimensions. From the
Yeah.
dimensions, I have calculated dimensions for this. These are the dimensions. But these are the dimensions, these are maximum dimensions. So we have, from those dimensions, we are not getting the accurate results. So we need to alter something, then the dimensions will change. So
Yes.
by altering something, so here you can see that we have gone for the surface current from where we got that, we are getting this from here, then we have put the slot here. So from here, from the dimensions, starting from the dimensions, means this is the maximum dimension. If we want to miniaturize, then we got for the slots, all those things. After that, we need to go
Okay.
from the standard formulas, we will get the standard results. We cannot miniaturize it, we cannot modify it. So if you want to alter the results or you need to miniaturize, then you need to just suppress your dimensions.
Yeah.
And
Yes, sir.
then you are going for the surface current, then again you need to simulate it. After that simulation, then you need to combine something, and from there you need to calculate the values here. Then you need to go for that equivalent circuit analysis, then compare with, then fabrication, then again compare. All those things you need to do.
Okay. Sir, just one more thing. Sir,
Yeah.
I've seen that many formulas are being defined here. Sir,
Yeah.
so suppose we want to publish a paper, sir. So can we just refer this formula and keep it
Yeah,
in
you
the
can refer. Yeah, you can refer these formulas.
Oh.
These are standard formulas. Here you can see that these are standard formulas are there.
Yes, sir.
Yes, in this 58, these are standard formulas. F1PW that you are getting from here, F32W that you are getting from here, from their Excel you can get it, from BCF you can get it. So from the directly you can get these values and these values from here.
Yeah. So and like for like for high quality journal, like maybe transactions,
Yeah,
then does the reviewer expect like something like empirical formula from the authors, or is it necessary?
No, these standard formula they may consider for those. If you are going to give some more than that, then it's very good for that.
Okay. Otherwise,
Like
also
here in this transaction, we have just given the standard,
okay. Okay, sir.
and
Thank
that
you.
is
And
the IEEE transaction on electromagnetic compatibility.
yeah, yes, sir. Sir, okay, sir, yeah, if you can please go to slide number 92.
92.
Yeah. And like I saw that for those parallel LC circuits.
This is 92.
Oh, I think maybe I got it slide number wrong. Like where you have the yeah, this one, sir. Sir, here you have L1, L2, L3. Similarly, C1, C2, C3. But
Yeah, here you
the
can see that the two parameters that I L1, L2, and means for the outer ring, for the middle ring, for the inner ring. That
yeah,
for
yes.
L1 that are
Mhm.
calculated from the dimensions that are dimensions from that is coming from this figure.
Yes, sir. Sir,
This
my
figure,
doubt.
this figure.
Yes, I got it, sir. So my doubt here is that, but the formula provided here is mentioned here is only C and L. So,
Yeah.
sir, how do we know that? Like, if we use this value, then our C value is going to be used for C1, and then if we give this
That
value, then
you for that, like for the higher for here in the figure you can see that from where we are getting this the surface current I have shown it. Yes, here 2.5 I am getting from the outer one, 3.5
yes,
from this one, and 5.5 that is getting from the
from
this
inner.
one. As
Okay,
for the as the frequency increases, size decreases. So the higher frequency that is we are getting from the inner part, and the lower frequency we are getting from the outer part.
okay. Oh, so sir, the basically the equivalent circuit is being defined using the surface current.
Yeah, no, not that is not for me. That is a general thing. Means for the lower frequency, for the lower size, the frequency is higher. For the higher size, the frequency is lower.
Yeah, yes, sir. I got that. But
And from here,
just
you can see that from this figure.
mm,
Just let
yes,
me.
sir.
Yeah, from here you can see that the dimension D19. Yes, you can directly see that.
Yes, sir. So my concern here is just that. Uh, we don't need to separately give the formula for L1 separately, then L2 separate formula, L3 separate formula.
No, these are or the same formulas are being used and same formulas are being and they are calculated here. These L and C are calculated from this formula only.
Yeah. Oh, okay. So P
Got
value
it?
is different from each thing. Okay. I got it. I got it. Thank you.
Okay.
Yeah, I got it, sir.
I think, sir, now there are no more questions.
Okay.
And sir, on behalf of EICT Academy and Electronics and Communication Department, sir, thank you very much for the lecture. This was very much interactive. And hopefully all the participants enjoyed the lecture and gained very much good things from this lecture, sir.
Okay. Thank you, Swati.
Thank you very much,
And
sir.
thank you, participants.
Dear participants, tomorrow is a holiday. Monday, we are going to start with the day 3 of this FDP. The session 1 will start from 9 a.m. sharp. You are requested to kindly join on time. Thank you. One more request to all the participants, those who have not registered on the Canvas, you are requested to please register on the Canvas by today itself. And if any participants find any issue, you can please ping on the WhatsApp group.